Hello and welcome to Chill Skills Sporlan Tech Talk. It's time to talk about this stuff. The topic for this episode is supermarket liquid line components, mechanical subcoolers, and liquid pressure regulators. If you've been paying attention, this is the fourth in a series of presentations that will follow the agenda of the old supermarket seminars. In the past, Sporlan had a team of professionals on a supermarket team. It's kind of interesting, a team on a team that went around the country to facilitate these presentations in person. With this Tech Talk entry, we're bringing the supermarket seminar concept back and hopefully servicing a bigger audience in the process. We've got an upcoming seminar. Yeah, I know those of you paying attention again realize that we've already presented webinars on solenoid valves. However, we're doing it here again to maintain the consistent cadence of the original Sporlan Supermarket Seminar. That means we'll discuss solenoid valves in March on the 19th, again for a nice review of these magical electromagnetic devices. Here are a few instructions. If the speaker on your computer doesn't work, you can simply dial in with your phone. It sounds like there's some people doing that. There should be a phone number somewhere on the invitation that you originally received for the webinar, and please mute your microphone. I was going to say something rude, like we really don't want to hear what you have to say, but that's not nice. As we move along and you have questions, type those questions into the Q&A window. We plan to answer questions live. If we run out of time to answer questions during the webinar, we'll post answers online. Hello, I'm Jim Jansen, Senior Application Engineer for the Sporlan application. My stunt double and technical backup today is Glenn Steinkaning. Glenn is a product manager in the marketing department, and he also collects a paycheck from Sporlan. You could always say hi, Glenn.
Well, hello, Jim.
You were supposed to say hi, Glenn. As I said, say hi. Okay, I got it. If you have any follow-up questions or feedback, you may contact us via email or contact Sporlan technical support team at svdtechsupport@parker.com, or you can always call 636-239-1111. Our individual emails are listed under our images there on the slide. Here's a schematic of the basic vapor compression refrigeration cycle. It includes four primary components: the compressor, condenser, metering device, and evaporator. Glenn, where can we learn more about this stuff?
Well, Jim, we've talked about this in prior modules of this exact same series. So we have those recordings out there. If you'd like to have more information on those, please go back and refer to those. And of course, every handbook of refrigeration or air conditioning has quite a bit of detail there as well.
Cool. Thanks, Glenn. And as we step through this, we've highlighted those primary components. They're circled, and they're important to every system, and every vapor compression refrigeration system is going to have some version of these components. The modern refrigeration system is advanced and can seem quite complicated. Each one's a little different. Here's an actual example. This is our Sporlan Medium Temp Rack B. Generally, these systems would include all four primary components that we just discussed. The compressor, the condenser, the metering device, the evaporator. This particular system, though, is a rack, and you can see there compressors and controls and oil level devices and such. Most systems will include one or more compressor racks in a mechanical room, maybe even with split suctions, intended to satisfy both low and medium temp refrigerated cases. And these systems may include different refrigerants, condenser types, unloading devices, subcoolers, heat reclaim and split condenser valves, head pressure controls, and lots of isolation valves. Here you can see compressors, control panels, an oil separator, oil reservoir, oil filter, oil level controls, and differential valves. And this particular system is indeed in our lab out here in Washington, Missouri. Here again is that multiplex system. And right now, we're simply going to highlight the part of the system that we plan to discuss today as we move on to discuss liquid line components in more detail. Downstream from the contaminant control, and here I might go ahead and use the laser pointer, but downstream from the contaminant control, we have a mechanical subcooler. Even though in this particular version, we're showing an EEV in the circuit. The term really refers to the mechanical nature of the heat exchanger used in this subsystem and not the flow control device. The rack's mechanical subcooler is typically a circuit on the rack or another rack at the supermarket. For increased efficiency, the low temp rack will be externally subcooled by a medium temp rack. Note that medium temp rack's not shown in this diagram, just to simplify. But again, using that laser pointer again, see the connection to the EEV from the medium temp rack, or from the medium temp liquid header, see the connection from the sport evaporator pressure regulating valve to the medium temp suction here. This allows the medium temp compressors to help with the low temp load. The medium temp compressors are typically more efficient compared to the low temp compressors. This is a compression ratio or pressure ratio thing. Most medium temp systems that utilize a subcooler are self-subcooled, as there is still a benefit to the subcooling effect even in this situation. Colder liquid fed to the store cases increases the refrigerant's net refrigerating effect, or NRE. What's NRE? Glenn, you're way smarter than me. Tell us about that.
Well, Jim, the net refrigerating effect is essentially how much energy can be transferred during the conversion from the liquid to the vapor and from one temperature to the other. So the net refrigerating effect is completely dependent upon both the evaporating condition, such as having a liquid line at 90 degrees and having an evaporator at 20 degrees. That will give a slightly different net refrigerating effect than, say, if it was a liquid temperature of 80 degrees or 100 degrees. So it's really that amount of energy that could be transferred during that phase change condition, as well as the sensible change from one temperature to the other.
Wow, that sounds pretty complicated to me. I'm going to look at it this way. Colder liquid means the refrigerant can absorb more heat. As a result, less mass flow of refrigerant must be circulated in the liquid line to meet case temperature. In this case, simply a Q dot equals M dot times delta H kind of deal. With the same heat transfer and an increased delta H, the M dot or flow rate could be reduced. This affects the TV selection as well, and generally reduces the suction and liquid line diameters. Smaller line sizes, smaller size diameters mean, well, smaller line sizes, and size matters and you spend less money. Controlled subcooling could mean a solid column of liquid is present at the TV inlet, with more success with setting the TV to control superheat. Insulation on the liquid line will likely need to be added to maintain the level of subcooling as the refrigerant flows throughout the relatively warm store. Now, we can kind of review this slide briefly and just look at the ratings of the TV with different liquid temperatures being introduced at its inlet. And we can see that subsequently the line size could change as a result. Here with 100-degree liquid with a standard 1-ton nominal valve, it's 84% loaded at the conditions that we've listed here. If the liquid temperature drops to 70 degrees, we can see that we could have a smaller nominal valve with about the same kind of percent rating, 89 versus 84. And if the liquid temperature drops clear down to 50, we can do this. We can do essentially the same job with a half-ton valve. Kind of an interesting situation. You're gaining an advantage here on the low temp rack and using higher pressure compressors to do the work. You could run the low temp rack to achieve the subcooling effect. You just wouldn't benefit from running the more efficient medium temp compressors to do that job, and subsequently wouldn't enjoy the potential energy savings that goes along with it. Many systems previously used mechanical subcoolers that were controlled by one multi-capacity TV or even two TVs in parallel, like you see here on this slide. These two TVs can be staged based upon varying loads, and the loads can vary a lot. In this example, the nominal 5-ton valve, that's the one shown right here. This 5-ton valve could handle one version of the load. For even lighter loads, we could switch to the 3-ton nominal valve And in the case that we had even higher loads, we could use both valves. Both valves could be utilized in that case. The mechanical EPR that you see right here controls subcooler pressure to help maintain consistent subcooler pressure and influence leaving liquid temperature. This subsystem evaporates liquid from the medium temp rack to cool or subcool, if you will, the liquid from the low temp rack. Obviously, this results in a change in temperature in the liquid flow to the low temp liquid header, ultimately improving system performance and operation. Remember, the medium temp rack is not being shown in this diagram for simplification. You can see the connection, the parallel bank of solenoid valves and TEVs from the medium temp header. See the connection from the sport evaporator pressure regulator back to the medium temp suction.
Hey, Jim, I think before we move on, we got
Yeah.
a really good question here.
Oh,
Can the liquid be subcooled too much?
Well, what are your thoughts on that?
Well, I do believe it could be potentially such that you actually would take the smallest valve and still have way too much capacity with that valve, and perhaps it would not control so well if the subcooling was drastically lower. But I think if you looked at the previous slide, remember we went from 100 degrees all the way down to 50 degrees.
You could do that.
And you did have to make a change to the valve sizing.
Yeah.
So I think you could actually throw off valve sizing if your
you went
subcooling
too
is
far.
too low.
I tell you, from what I've seen, 50 degrees seems to be the low end of what makes practical sense in many instances. But there may be times where there's some benefit to go lower than that, but I think you've got to be careful with the selection of all the components that are involved. Here's a slightly different version. Instead of mechanically functioning thermostatic expansion valves, we have an electronically controlled, electrically actuated option for the subcooler. These exist today to control leaving liquid temperature and arguably do a pretty good job, maybe even more accurately than the TEV version. Here, the Kelvin subcool control depicted maintains leaving liquid temperature while monitoring subcooler superheat for compressor protection. Provided the subcooler is meeting the design liquid temperature, the superheat is allowed to increase or rise. If the superheat falls below the minimum set point, the leaving liquid temperature is disregarded in order to maintain minimum superheat. That's just a detail in the controller algorithm. There's also sort of a hidden note down here on the bottom of the slide. It says to close short across the dry contact terminals 25 and 26, and periodic reinitialization is recommended. This is really a Kelvin control detail. And we have some really good videos posted on YouTube for installation and setup of Kelvin controllers. Take a look at that. And remember, we're not showing the medium temp rack in this schematic to simplify it. And again, see the connection to the EEV from the medium temp liquid header. That's this line right here. And see the connection from the sport evaporator pressure regulating valve to the medium temp suction. Also, for those of you who've got a lot of experience with these sort of things, there is a variation of this system which will deploy a CDS valve in lieu of the sport and include a TEV, mechanical TEV, in lieu of the EEV. Which combination is better? I don't know. Beats me. I think they both have their place. And did you want to add something? I mean, you're bugging me, Glenn, here. You act like you want to talk.
Well, Jim, don't forget, we're subcooling that liquid going to those TEVs on the low temp side. So of course that can result in more energy savings, cost savings, and just add to the overall benefit of this style design.
That's a good point. Let's move on here. Wow, this really kind of brings everything together. Here's a comparison between that mechanical TEV-based version, which might have a tolerance of subcooled liquid of anywhere from plus 12 to minus 12 degrees, and EV-based control, which can generally keep it a little tighter, plus or minus 3 degrees F. There are benefits of not only controlling the level of subcooling the liquid, but benefits of a consistently controlled, steady level as well. And this chart really tells that story. This data was acquired in our supermarket lab on an actual production rack. We compared the performance of a mechanical subcooler with two appropriately staged TVs with solenoid valves to direct the refrigerant flow to the performance of the same rack equipped with a single EEV and Kelvin style controller. With the set point of 50 degrees F, the mechanical subcooler experiences a much wider fluctuation in outlet temperature control as compared to the same system fitted with an electronically actuated, electronically controlled expansion valve. Now, either system will subcool the liquid, but the EEV version can do it with a more consistent liquid temperature. Ultimately, the more stable the liquid temperature being supplied to the expansion devices at the refrigerated case, the more stable will be the control of the refrigerated case in general. Does that make sense?
Does to me, Jim, but we do have a few questions. If you
Oh,
wanted
no.
to try and
Questions?
answer a few of them. I'll go ahead and answer one of them. On the
Okay.
EEV we're talking about here, this was actually a stepper motor type valve, not a pulse width modulated valve. And so that's answers that question. And then the question about is a sport EPR recommended over an electronic CDS valve?
It depends. And if you remember, I said, and I'll back up to that one slide, this is one way to set this up, as you can see here. There's the SCR valve, which fills a row of the EEV, and here's a sport, R sort, mechanical EPR. There are systems that utilize a CDS in place of the sport valve and a mechanical TEV in place of the SCR. Generally speaking, you wouldn't necessarily have a CDS coupled with an SCR, but I suppose one could do that if you were so inclined.
There's a question, could you have more than one subcooler in a loop? And why would we ever want to do that? The only reason it would make sense to do that is if you did not have a large enough evaporator available to meet that to meet that need, and so you have to put two of them in series or two in parallel. But that's really not what we see in practicality. In general, it's just a one unit. And one other question: we're showing liquid from the medium temp rack to subcool the low temp liquid. Could you just not use the low temp liquid to do the same thing?
And in fact, we mentioned that earlier. Absolutely, you can. What you end up doing, though, is working those lower pressure, lower temperature compressors to do the work. And generally, they might not be as efficient as the medium temp versions, and you don't get the same kind of cost savings. But functionally, yeah, you could do that.
Sure. So it's all about cost savings using medium temp instead of the low temp, whether it's using low temp suction gas.
Well, it's about cost savings and about stable control. It's a combination.
Okay.
Here's a slide that we've included on troubleshooting the subcoolers. I've been talking a lot. Glenn, would you like to make some comments on this?
You know, subcoolers are really not that complex. You know, so there's really only two things that can be going wrong. You're not maintaining your liquid temperature properly. Obviously, they're going to look at those sorts of things as we show here. Make sure you have the right TEVs that are working properly. Make sure you're pulling the right solenoid on at the right times for the right capacity. And then check that subcool control. And then for the liquid returning back to the compressors, obviously that's a superheat issue. And go take a look at those EEVs and TEVs, and then troubleshoot those as you need to make sure you get it back to proper and superheat.
Sounds good. We're moving on to the next phase of this tech talk, and here we plan to include a few comments regarding something known as the Liquid Pressure Regulator, or LPR. It's installed in the liquid line to provide consistent outlet pressure to the TEVs. With a steady supply of stable temperature and pressures, setting those mechanical TEVs at the refrigerated case becomes an easier and more reliable proposition. You're stacking the odds in your favor of the thermostatic expansion valve's ability to control the desired superheat at the outlet of the evaporator coil, presumably where the bulb and equalizer have been installed, and hence have just better stable overall control. There is the LPR indicated there. And sometimes that's referred to as a liquid header pressure regulator, as we'll learn why that might be the case. This is an overview of the purpose of that valve. Liquid pressures change throughout the year due to ambient conditions. Fluctuations cause TEV loading to change and the TEV to potentially hunt. That LPR is used to minimize liquid pressure fluctuations. And that's where the liquid header pressure regulator moniker comes in. It receives liquid from the receiver and supplies refrigerant to the liquid header and maintains a stable pressure. Keep in mind, at some point in time in the future, we plan to host a series of webinars covering the refrigerating specialty division's Flowcon product line, which we have part of that depicted here in this slide. There exists a complete product line of these valves that are used throughout industrial refrigeration systems and applications. So stay tuned. We'll have those scheduled sometime in the future. Here, while the head pressure control, traditional head pressure controls maintain a minimum head pressure to prevent starving the liquid line devices, the liquid header pressure regulator acts to control the peaks of head pressure that might occur in, say, the summer months. The low percent loading of the TEV that could subsequently occur in the summer months, in the case of this example, we show as low as 49%, could result in a flooded condition because the TEV is relatively oversized when that happens. This situation could ultimately be detrimental to system performance and maybe even system life. Over here, we see winter with a subcooler and the accompanying percent loading. And over here, summer conditions with a, what is that SC there? Subcooler. That's the thing we talked about a little earlier.
Yep.
And the LPR, the liquid pressure regulator, look at the stable percent loading that we have on the expansion valve in this case. And comparing 100% loading versus 49.
Obviously, the valve's going to operate much better in that sort of range, Jim.
Sounds good to me. Here's a cutaway of the LPR, as it's called. Same operation as receiver pressurization valve. It regulates outlet pressure only. This can be the refrigerating specialties A8 or A9. And I hate to say it, unless we've got some other questions, we're starting to run in towards the end of this. We're kind of wrapping it up. You can view an encore performance of this webinar on Facebook or YouTube. It'll appear on our Facebook page first and on the YouTube channel a little later. Eventually, it'll be out there for you to view again or to see for the first time.
And Jim, we do actually have some questions
that
we haven't answered yet.
Okay.
Looks like we've got 4 or 5 of them here.
4 or 5.
So how about we hit the easy one?
Apparently, they've figured out something I don't even need to comment on here. So What do you got? I'm going to put it back here to the stay connected slide so they can maybe make some notes of that. They know how to contact tech support if we can't answer their questions here. By the way, if we don't get to a question that you posted, we will post an answer online at some point in the near future.
Yep. So we'll start with an easy one, Jim. How critical is the liquid line insulation to the liquid subcooling? How much temperature gain can the liquid suffer if the insulation is poor?
I think that's a very valid point, and it's great. In fact, if you've gone to the trouble to put a subcooler in place and you've got low temperature liquid flowing through it, that's a good bet you're going through a warm temperature store with the routing of the liquid line. It's really good practice, and in fact, something that I should have mentioned along the way, that insulation of that line is fairly critical. That's a good thing to do. Or if, in the case of, to use that technical term, if the insulation is lousy, maybe you'd want to go to the trouble to replace it. You get any more questions there?
We sure do. Does a mechanical subcooler have to have an EPR valve, or could you simply cycle the solenoids off of outlet temperature only?
Well, there's all kinds of different ways to achieve temperature control. What we've done is in this slide presentation is depict two common methods that we are seeing, and they're two methods that we've scrutinized in our lab. I'm not going to say that there's not other ways to get the job done.
All right.
What else do you have? Do you have another question?
We do.
What is this?
Do TEVs tend to fail closed if liquid supply pressure is too low?
All right. Well, that's kind of a loaded question. Here's my thoughts on TEV operation. There's three things that tend to tell a TEV what to do. It's the pressure that's generated in the bulb that tends to open it, and the pressure generated by, and the way our valves are designed, a closing spring that's located in the bowels of the valve, and then the feedback from the suction line known as a equalizer pressure. That's kind of misnamed in a way, but that tends to close the valve. So it really depends on the balance of forces between those three characteristics. And ultimately, if the liquid supply pressure is low, what's happening with those other parameters? You really have to look at it as a whole package in order to say, is the valve tending to be closed or not?
Mm-hmm.
Do you have anything else you'd want to shed on that?
Nope, that sounds like it. It's that evaporator outlet pressure that is the biggest concern. And we just had some questions. With the better control using EEVs, is the LPR still useful?
I think so. The LPR, the question is, can you, I guess what they're inferring, could you get rid of the LPR? And because of the function of the liquid pressure regulator, it's trying to establish a maximum level. And while an EEV approach might be less sensitive to that, I guess you can make the argument that it is somewhat irrelevant, but again, I think you're stacking the odds in your favor if you shave off the peaks. But other folks may have a different point of view on that.
All right. I think that's all of the questions, Jim. We'd like to thank everybody for their participation.
And again, just as a reminder, we're going to do another webinar on March 19th. We're going to cover solenoid valves once again to stay in the cadence of the supermarket seminars. And this concludes our presentation on subcoolers and liquid pressure regulators. Thanks for helping today, Glenn. I couldn't have done it without you.
Well, it's good to be a part of a team, Jim.
Thanks.